Hi, I'm Damien. I'm a hardware TLM with Meta. Today, I'm joined by Bharat, Technical Sourcing Manager of Meta, and Jay, CVP of AMD, to talk about Meta's AMD one-socket server, and as well as how do we scale for performance efficiency. We built this AMD one-socket server on Yosemite V2 platform. This platform, when we developed 3 years ago and contributed to OCP, is CPU agnostic. It's architected to be that way. And this is scalable, flexible. It can support 4 microservers in a sled, or it can support 2 microservers, 2 carrier card in a sled, and of course, the NIC can be changed to accommodate different speed. It is a high-density microserver. Configuration in the 4OU, we can get up to 16 microserver in this configuration. And today, we'd like to announce that the North Dome AMD CPU module will be supported on this platform. Let's take a deeper look into North Dome itself. The CPU is based on AMD SP3 socket, whereby Meta tests it with the 3rd generation EPC CPU. It has 6 channels of DDR4 operating up to 3200 megatransfer per second. It has 2 storage devices, both in M.2 form factor, but one is 2280 and another is 22110. Both of it connected through the NVMe bifault link. As for other expansion features, they are pinned out through the Goldfinger onto the baseboard. We have PCIe, USB, I2C, as well as UI connectivity. And you can see from the picture, all the features are actually on the top side, except for the storage, whereby they are at the back side of this design. A little bit more detail about North Dome block diagram. I will highlight the key features. How do we know whether this plug into the baseboard is server card or device card? It is coming through the card type communication, but how do we know whether this is a AMD or something else? It's based on the bridge IC. You will communicate with the BMC to know about that. And when we architected this for AMD CPU, we realized that we need to use bridge IC and the CPU will be communicating through the APML interface. And of course, for AMD CPU, if you knew anything on the debug side, we'll be using the HDD port. On other areas, such as the general power sensing, the through EEPROM, the TPM, or the BIOS flash, they are virtually similar to the one that we had contributed 3 years ago. Currently, this spec has been discussed in the server group, and if you go into the server wiki, you'll be able to find the draft spec. We're going to contribute this officially to OCP in next month IC meeting. And as for the design, like schematic, layout, the BOM list, the firmwares will be contributed by our ODM in a couple months. And for now, I would like to pass it to Bharat and Jay and to talk about how AMD optimized the CPU to suit Meta needs. Thank you.
Thanks, Damien.
Thank you, Damien.
I'm Jay Kirkland, and I happen to be very fortunate to be able to run the platform engineering team for AMD server group, so everything EPYC, and very happy to be here.
Yeah, and as I just mentioned, I'm Bharat Mutaya. I'm part of the infrastructure team at Meta.
Yeah, so I thought we'd start by, Bharat, if you could talk to us in more detail about what your real rack and server requirements are in order to deliver everything that Damien's talking about in terms of the value promise. So could you talk a little bit about that?
As we have kind of gone through in a couple of sessions earlier today, Facebook, starting from maybe around 2015-16, has been leading the charge in terms of transition to single socket servers and has multiple contributions to the OCP space, starting with Yosemite V1 in 2015-16, Yosemite V2 in 2017, and then Yosemite V3 that Kiran and Todd covered today in 2020. The basic premise of the architecture is to make sure we have highly dense form factors which enable excellent rack level performance, And over time, we have also used the architecture, like Kiran and Todd mentioned, to support more modularized configurations of both flashes as well as accelerators into use cases such as video transcoding and AI inference. So that is the general philosophy with which we approach our compute offerings, and that's kind of what drives our compute requirements.
Okay. You know, we've talked about this a lot the last year plus, right?
Yes.
And I think it'd be good for everybody to hear from you what you've been telling us that you really need in the CPU itself in order to meet those requirements.
Absolutely. So when we started working on this with AMD, we saw a lot of promise with the chiplet-based architecture that AMD was pursuing. And some of the key requirements for us was to figure out how this innovation could be adapted to our key optimization points. Specifically, we wanted AMD to focus on how to get these chiplets to focus into a much more performance per watt efficient, lower TDP standpoint. And then as Todd and Kiran covered, there are strict density requirements for us from a platform standpoint. So we really wanted to make sure that the footprint of these compute offerings would fit into our existing platform. So the challenge was to see how the EPYC family of CPUs, the third generation, could fit into our Yosemite V2 platform. And we really were after best-in-class performance per watt efficiency, so there were strong requirements around the types of performance that we would need this offering to hit. And lastly, in order to meet cloud scale time, we cannot afford to have multiple SKUs for different TDP points. So we really wanted to have much more granular power control so we can figure out for our workloads what the best efficiency point is. So these were all the primary macro level requirements we wanted both the Meta and the AMD engineering teams to collaborate on.
Yeah, very good. I've heard this over and over continuously the last few months and last year, so that was consistent.
Right. So now I want to maybe turn it to you, Jay, to discuss how we went about this. But maybe before we spend time focusing on the meta-specific optimization that AMD did, for the audience, you may want to start with calibrating on the EPYC third-gen processor and the capabilities it brings.
Okay, sounds good. Thank you. So our AMD engineers really love challenging the status quo and changing that pace of innovation. And it really makes for an exciting day in the office every day as we talk about these things. And certainly in 2017, when we released our first generation EPYC product called Naples as a multi-chip module, we really disrupted the industry by exploding in the core count, increasing the I/O capacity, expanding the memory bandwidth all at one time through this multi-chip modular architectural approach. And then we quickly follow that up, as a lot of you know, with Rome, where through this architecture, we're able to quickly get PCIe 4 out well before anybody else did. But more important than that, we're able to mix and match process nodes on the same substrate, which enabled us with Rome to have very performance efficient operation up to 64 cores, which was well ahead of where the industry was, probably 3 to 4 years ahead of where things were. And then we fast forward to March of this year with our Milan product, that same architecture, we're able to drop in a brand new microarchitecture to that and see our performance for all of our customers over the last few months be 19+% increased. You know, we did this through much better IPC efficiency, as well as what we call dynamic range, which is the ability to scale across different workloads and different power points, our performance very, very efficiently. So if we dive into that, you know, a little more, you look at, you know, what did we do with our cache organization, for example. We said, hey, a larger L3 cache from our learnings from our first 2 generations could help a lot of our workloads. So we actually changed the structure somewhat and coupled together 8 cores versus 4 cores, and we're seeing major boost and you know, lowering affected memory efficiency or memory latency because of that. In addition to that, a lot of our customers now are starting to use EPYC for their inferencing workloads. So for this generation of Milan, we actually doubled our Int8 performance. And that has been, you know, allowing us to power our customers in ways that we were not able to before. But you know, the thing I like the most about our EPYC architecture is that we truly can move fast when our customers, such as Meta, come to us and say, hey, we have this specific business need. And one thing about AMD, since I've been here, that I've been most impressed and I'm most proud about is how we truly listen to the customer requirements. And now with this architecture, we actually have a vehicle to deliver a rate of innovation that has never been delivered before.
Yep, talking about listening to customers, so let's maybe switch gears a little bit into discussing how the engineering teams at Meta and AMD collaborated on meeting some of the unique requirements we had for the North Dome platform, Jay.
Yeah, that's a good question too. So first of all, let me tell you a little bit about our Topa Stack offering from Milan. It's a 280-watt offering at 64 cores. Now, as you heard earlier, we have a power envelope of 95 watts for North Dome that we had to operate in. And these guys kept us true to it all the way along the way. So that's a far cry from 280 watts. But again, because of the dynamic range of our Zen 3 and the modular architecture that we have, we knew it was possible to get there with hard work and collaboration. Now, one thing I did want to pause and talk about is, all modular architectures aren't created equal. A chiplet architectures or chiplet technology coupled with, doubling down on packaged substrate technology is a beginning. But what you really need to have if you're going to have a scalable architecture is to be thinking about this, from the early concept days to design to development, even customer support, so that you can provide tools and you can train customers on how to eke out every bit of performance out of this. And this is what we did. We started off on the right foot of actually training the Meta engineers on everything about our architecture, everything about our tools, understanding their requirements. And now I'd say a lot of these folks know as much about what they can get out of our CPU as we do. And we landed together, right, on a 36-core, 95-watt SKU that's very, very efficient and delivers the density that Bharath was talking about.
Absolutely.
But most importantly, it delivers amazing performance per core so that we don't have any of these latency concerns. So this has been, really exciting to see this delivered in North Dome, and now this being offered to the OCP community to innovate on top of, because we have a lot of momentum, and to see what the OCP community can do along with that as we release this.
Absolutely. I think that's kind of the most exciting piece of it. So maybe let's switch gears to talk about the joint investments that both Meta and AMD did in the space and the areas that we want to open up for the industry to collaborate on this going forward.
Yeah, let me just cover this real quickly, right? So first of all, like I said, I'm excited you'll be able to get access to the specifications in North Dome. And I'll say this, that our engineers are always inspired working with Meta because of this commitment to be green and power efficiency is everything. And because of that, this type of work, this hard work that has been done between the teams is something that's perfect for OCP and perfect for us to, go off and build on top of. Now, of course, power, 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 that was the whole mantra, right? So what we had to do is we had to say, what are our power management algorithms that need to change? What are our power delivery mechanisms that have to change? How do we meet those together? And looking for every aspect between firmware tuning, electrical characterization, anything at the system level that could actually impact this down to the chip level. So there was a lot of collaboration just on that power management perspective. But since I mentioned system, one thing we said from the beginning, and we worked on this very early, was anything in the system we could challenge. Right, so early on it was part placement on North Dome. Did that match what we needed to do? It was layouts. It was BIOS algorithms. Anything in the system we worked together on, and then finally I'll say that at the software stack level, we looked from everything from general things that would help a North Dome platform at the OS level, to more specific workloads that Meta identified, maybe in web tier or certain databases that you thought would be appropriate. We pushed on what could we do in inferencing and AI on the platform by training folks on our Zen DNN library that's good for that. And we also did a lot of work together on saying what could we do to advance compiler technology with LLVM and our own proprietary AMD stack on compilers that actually leverages a lot of that work. So all in all, I just want to say that all of this now being available for all of you and the whole OCP community to build on is super exciting, and I just can't wait to see what comes out of this and how we're going to have the best, most power-efficient servers, in the world as a result of this work on Epic and this work together with Meta. So, why don't you tell us what our call to action is, Bharath, and then we'll
Yes, Damien alluded, the specifications are on their way, and we have collaborated on our single socket servers for a long time now, and we look forward to extending the collaborations with AMD going forward. And we invite all participants here to join us on this journey. And again, I want to thank Jay and the AMD team for the partnership.
Yeah, thank you, Bharath. This has been a wonderful experience.
Thank you.